Let's talk about Newton's laws. That apparently is what Isaac Newton looked like, at least at some point in his life. Actually, the thing about Isaac Newton in this context is that he's actually most famous for his writings on subjects like religion, philosophy, mathematics, much more than the things he said about physics per se. However, in this, what we're looking at is his famous 3 laws. These are some of the simplest descriptions I can give you of what his laws said. They aren't quite the way he said them. For example, the second law, the way we usually learn it, is about a net unbalanced force and acceleration being proportional to the size of the force. But Newton actually described this in terms of impulse and changes in momentum rather than accelerations and forces. Nevertheless, it's equivalent mathematically to this description. It's worth keeping in mind that actually these are laws, and in the context of the way we look at physical things, facts, hypotheses, theories, laws, the fact is what you observe. The hypothesis is your educated guess about what's going to happen next based on your observations. If you do hypotheses and do enough tests to verify your hypotheses are right, you can come up with a theory, which is your summary trying to explain what you think is going to happen on the basis of your testing. And if you have a theory that lasts long enough and no one can contradict, all the experiments we do support your theory, then we can turn it into a law. The law is about a set of observations that we say, that we see always happen, no known exceptions. And it's particularly important to note that the law explains what's happening. It doesn't say anything about why necessarily. And of course, to add to this, we're talking about Newton's laws. In fact, we know that some of Newton's laws aren't quite true, especially the second law. But the only context where we know it breaks down, I guess there's 2. There's relativity when you get very close to the speed of light, and there's quantum mechanics at the very small scales. The things we observe in the universe around us don't actually happen that way. However, in day-to-day life, you are going to see Newton's laws being well supported by your observations. So let's look at them carefully. Newton's first law says every object remains in a state of rest or of uniform motion in a straight line unless acted upon by a net unbalanced force. Now, we've talked about the state of rest before. The state of rest is where, if the forces are balanced, then all the forces acting on it are in balance and the object stays where it is, remains stationary. But Newton's first law actually points to another possibility. Again, if you have net balanced forces, no resultant force, you can be in what's called dynamic equilibrium, where you are moving in a straight line at a constant speed, but you're not stationary. In fact, relativity goes a step further and says, actually, there's no difference between these 2 points of view. There is no official state of rest. But we're saving that discussion for later. So Newton's first law talks about static equilibrium, when all the forces are in balance and it remains stationary, or dynamic equilibrium, where all the forces are balanced and it keeps moving in a straight line at constant velocity. So both of these are when the net force is 0. The opposite of this, or the counter side of this, is when the forces are unbalanced, in which case something else is going to happen. and that something else is described by Newton's second law. Newton's second law says, when a net unbalanced force is applied, the object will accelerate proportional to the size of the force, and it's in the same direction as the force. So a net unbalanced force produces acceleration proportional to the force. And this is how we write that. The acceleration is proportional to the force. That's not quite the way we usually remember it as an equation nowadays, though. We actually have it the other way around, and that's okay. If acceleration is proportional to force, then force is proportional to acceleration. And I can write that, therefore, as force equals some constant times the acceleration. And we call that constant of proportionality, we call it the mass. Actually, that's not quite true. When we experiment, we determine that the mass works in this formula exactly like this if we happen to use meters per second and kilograms, and we get newtons. And that's related to what the Newton unit definition was, which was kilograms meters per second. And that's where that comes from. Now, applying Newton's second law in simple situations is very straightforward. You'll have two of the force, the mass, or the acceleration, and you'll have to calculate the third. Very straightforward. It's actually Newton's third law that students usually find most difficult to get a grasp on. Newton's third law says, whenever an object applies a force to a second object, the second object applies an opposing force of equal magnitude to the first object. Opposing means opposite direction, and it's the same size. So whenever something pushes on another object, that second object pushes back, opposite direction, same amount of force. Consider, for example, a block of chocolate resting on a table. Now, this block of chocolate is feeling the effects of gravity, pulling it downwards. That's its weight force. But the block of chocolate doesn't sink down through the table. So the table must be holding it up. And because it's stationary, it's in static equilibrium, that means the two forces are balanced. The weight force pulls down, and the reaction force, that's what we call it, the reaction force from the table pushes the chocolate bar back up again. The same magnitude, but the opposite direction. That force is called the normal force, or the normal reaction force, or the reaction force. I actually do prefer to use an R for that simply because, rather than an N, because if you put N for normal force, you end up with N for the name of the force here and N here for the newtons, for the units. Can get confusing. Be careful. That's what happens if the chocolate bar is just resting on the table. But what happens if I push down on that chocolate bar even harder? Well, let's have a look. Here's a block of, this one's a brick. Here's a brick resting on the table. Its weight force pushes down on the table, 40 newtons. But as well as that, the hand on top is pushing down harder with an extra 30 newtons. So the total force pushing down on the table then is 70 newtons. And that means the reaction force pushing back up on the brick is going to be that total 70 newtons. It's the equilibrant that stops the brick from moving. And of course, if we push down on that brick at a different angle, then we have to do some trigonometry to work out the reaction force. I'm pushing it at 30 newtons, but I'm pushing it at an angle of 30 degrees from horizontal, which means that's 30 degrees. So the force that's actually pushing downwards on the table is 30 for the force sine 30 degrees, which is 15 newtons. So the weight force 40 newtons and the additional 15 newtons pushing down produces a reaction force of 55 newtons pushing up. Now, of course, there's also a horizontal component to this force, pushing the brick sideways. It's not shown here, but the result of that would be the brick moving unless there's an opposing force called friction. I'm going to leave friction for another video.